Hello, everyone. Thank you very much for joining us, either in person or remotely through Zoom. We are really thrilled to have all of you here. My name is Anna Ogorzałek. I work at NASA Goddard. I'm one of the people behind LEM, and we're really excited to share with you the mission, what it's about, and how you can get involved. And our first talk is going to be by Ralph Kraft, who is the PI of the mission. So I'll just let him take over. And if you are on Zoom and are having any problems, please let us know in the chat. And also please put your questions in the chat.
Okay, thank you, Anna. Again, for those of you who don't know me, my name is Ralph Kraft. I'm a senior astrophysicist at the Smithsonian Astrophysical Observatory. And on behalf of Caroline and the rest of the LEM team, I'm very happy to talk to you about our probe mission concept today. I just want to start off and put everybody on the same page to make sure everybody understands what the probes are. The probe is a new mission line for astrophysics that was recommended by the Astro 2020 Decadal that's now being pushed forward by NASA. This is a $1 billion cost cap mission, PI led. And today I'm going to tell you a little bit about our concept. But before I actually talk about the concept, I want to just step back and talk about science a little bit. There we go. Okay, thank you. Talk about science at a very high level for a second before we talk about any missions or instrumentation or anything. And when we think about the astrophysics landscape of the 2020s and 2030s, and we think about what the big picture questions are, clearly one of them is this issue of formation of structure. Why does the universe look the way that it does today? Why do galaxies and stars and planets form in clusters of galaxies? There's a lot of people working in this area, obviously, on all kinds of structures and spatial scales. And this issue in the decadal was essentially under this broad rubric called cosmic ecosystems. It's clear that basically whatever's going on in the galaxies, the relationship between the stars and the central supermassive black hole and the hot gas, everything at some level affects everything else. And it's clear that this is a discovery area that's outlined by the decadal. This just isn't me saying this. There's a large segment of the astrophysical community that says this as well too. And so in the case of the galaxies, for example, here you can see that the modern day galaxies are of course impacted by the black hole and the stars, but we know that the galaxies have this very extended hot gas halo that is basically unobservable with the current generation of X-ray observatories. And if we're going to make some major advances in how galaxies form and evolve, I think it's critical to understand the relationship of this halo, or larger scale, to the rest of the galaxy. Likewise, in terms of the formation of structure of larger mass objects, this is yet another quote that I've just cut from the decadal, but you can see that the cosmological simulations of cluster formation also predict these filaments and this web of structure that fuels the ongoing growth of these more massive formations. There's not a great deal known about these filaments observationally. They're sort of very common in simulations, of course, but constraining the temperature, the elemental abundance, the entropies, and these structures would be a critical advance in our understanding of the formation of structure. So one element of the decadal, I'm going to just show one more slide here, is that some of these basic questions, you can sort of view the decadal as an STM. I mean, what are the big questions here about how galaxies and gas and dust flow in and out of the galaxies? Same questions can be asked for the more massive systems and how do the histories of galaxies and their dark matter halo shape the observable properties. The fundamental question here is what kind of information, what kind of instrumentation, do we need to make major advances in these scientific areas, okay? And, in the case of galaxy halos, and in the case of these cluster filaments, of course, these are all the temperature of these things. This is a few million degrees. They're going to emit in the emission lines of oxygen, iron, and other lines. So an X-ray instrumentation is pretty much a requirement here to make a major advance in this area. But not just any X-ray instrument. I mean, you really have to develop one that's optimized for the science, because this is you're essentially talking about very low surface brightness, very extended over tens of arc minutes or even degrees X-ray emission. And so the way to do this is to essentially develop an X-ray observatory that has a very wide field of view with an X-ray microcalorimeter at the focal plane. The wide field of view is a requirement so that you can efficiently map the galaxy halos, these filaments, these very large structures in a reasonable amount of time. And the X-ray microcalorimeter is an absolute requirement because you need to separate the redshift and emission lines from the oxygen, the iron, and the other elemental components from the very bright galactic foreground from the Milky Way halo and the local hot bubble. I'll demonstrate this a little bit more as I go on here. So this is essentially our probe concept. This is the concept of line emission mapper. The instrument architecture is as follows. So the concept is optimized to study large-scale, low-surface brightness diffuse emission in the 0.2 to 2 keV band. Has a very large field of view, roughly 40 times the field of view of the Athena Xiphu, with X and M-like imaging, The focal plane is an X-ray calorimeter with 15 arc-second pixels, and we're baselining 2 EV resolution over most of the array with a 1 EV spectral resolution, about 0.9 EV in the center. And this is optimized as a mapping instrument. The primary science will be achieved via directed program of selected galaxies, cluster filaments, and other galactic structures in the Milky Way halo. One thing I want to emphasize, and I'll get back to this, of course, is that the talks today, we only have a limited amount of time to talk about the LEM science, and we're going to talk about the science drivers that are driving the STM and the mission architecture. There's a very wide space for guest observer observations outside of the primary science, and I want to emphasize that to everybody that's in the audience. So when you're thinking about the future of X-ray astronomy, and if your science doesn't quite fit in here, there's a great many things in terms of AGN, star forming regions, stellar astrophysics, basically every area of X-ray astronomy there's also many investigations that could be done with LEM in these areas. So this is just a schematic diagram of LEM, pretty simple, an X-ray optic at one end, focal plane in the other, and we're looking at diffuse structures in our galaxies like the Fermi bubble, gas around nearby galaxies in a sort of a redshift range of 0.01 to about 0.03 or 0.04, and then gas beyond the galaxies in the filamentary structure. Okay, these are the LEM technical capabilities. Our baseline optic is a platinum-coated silicon metashell X-ray optic. We have roughly 1,500 square centimeters at 0.5 kV, so around the oxygen lines. This is several times the effective area of Chandra at the beginning of the mission. We require relatively modest angular resolution of 10 arcseconds to be able to remove the bright AGN, the brightest of the AGN, to not contaminate our background too much. The individual metashells have already demonstrated 2.7 arcseconds resolution at much higher energy in the lab. And there are definitely some technical challenges associated with scaling this optics technology up to the required area for LEM, but we think that they're certainly manageable within the cost cap of a probe mission. The focal plane detector is going to be a transition edge sensor microcalorimeter that has derived direct heritage from the Athena Xifu. So again, the technology risks of this are relatively low. Each TES will have a 2x2 hydra, so we'll have 64 by 64 of the TESs. Each has a 2x2 hydra, so extending our focal plane out to the required 30 arc minutes by 30 arc minutes. One difference with the Xifu is that these absorbers will be thinner than the Xifu absorbers, and they're optimized for performance in the low X-ray band, below 2 keV. This is just a direct comparison of some of the missions between LEM, CRISM, and Athena, for example. And you can see here that, I'm just going to use the pointer real quick. Athena has a lot more effective area, of course, than LEM around the iron or around the oxygen K lines here. But the grasp, LEM has more than an order of magnitude grasp than LEM, so it can very efficiently map these large-scale diffuse structures. Athena is really optimized for slightly different science. And this is the upcoming CRISM mission as well, too, that's going to do great things with the calorimeter, of course, but the total grasp, some of the science here is sort of well outside the capabilities of CRISM. Okay, this is just a plot on the left. Again, it's effective area. Again, you can see that Athena has considerably more total effective area of LEM. This is about the maximum effective area I think that we can fit within LEM, and comfortably fit within $1 billion mission. Obviously, we'd like to have more effective area and drive this up, but we definitely want to fit within the cost cap. But again, here, this is the grasp. This is the solid angle times the effective area that you can see that we have more than an order of magnitude effective area or grasp relative to Athena and a lot more relative to CRISM. Okay, so this is our science. Basically, with that, we envision the exact divide between geo and directed is definitely to be determined. But you can consider maybe a 50-50 division might be a reasonable way to start. That our goal is to make direct imaging of the hot gas in nearby Milky Way-like galaxies. This is really the missing link in our understanding of galaxy formation. I mean, this will provide us essentially a profound change in our understanding about how galaxies form and how galaxies evolve. As far as the simulators are concerned, I think that these are basic. Whatever's going on in the halo is largely unconstrained from any direct observations. We'll also get direct imaging of mass assembly in the outskirts of clusters, mapping of large-scale diffuse features in the Milky Way, such as supernova remnants, galactic structures. One of the things that the LEM team, I think, is talking about is very exciting is considering the scientific return of a survey. This could be maybe some mosaic of one or a couple of regions of the sky to look at the Milky Way and other really large, many degree scale objects, or maybe even doing an all-sky survey. I don't know what we're going to do here yet, but certainly members of the science working group are very excited about this, and we're looking at the possibility of this. Again, I want to emphasize that I'm emphasizing, and the talks today are going to emphasize some of the key science areas, but there's a huge space for geo observations. All right, let me just show you the capabilities of LEM here real quick, okay? This is a mock LEM observation from a simulated galaxy taken from the illustrious TMG 50 simulations. You can see the stellar component here, the spiral galaxy is here in the center. This is what it would look like, a 1 megasecond observation with LEM would look like, and this is in the oxygen 7 forbidden line, this is in the oxygen 8 line, and this is in the iron 17 line. So you can see we're essentially getting direct imaging out to 150 or 200 kiloparsecs out to R500, mapping an emission. And for example, the ratio of this map to this map immediately gives you the temperature distribution over the whole field. The ratio of this map to this map gives you the fractional abundance of iron to oxygen over the entire field. So we're mapping the temperature, the density, the entropy, the elemental abundance, essentially out to R500. And this is one galaxy in one relative, relatively moderate observation. This is why we need the microcalorimeter. This is a simulation of essentially all of the background components. You can see that the red lines here are the sky background, the instrumental background, the unresolved AGN background. For one of these simulated galaxies, this is from 0.3 to 0.6 R200 up to 80 to 100 kiloparsecs. The emission lines in green here are the emission lines from the redshifted galaxy. So without the calorimeter resolution, without the 2 eV resolution, these lines would be blended with these enormously bright lines from the Milky Way local hot bubble and the Milky Way halo. And this is why the calorimeter is absolutely crucial to be able to resolve these structures. 2 more? Okay, sounds good. Thank you, Anna. I may run a minute or so over at the end, but cut into question time. This is another comparison. You can imagine a notional large area X-ray mission with silicon detectors. And if we look at the same galaxy with LEM, with 2 eV resolution, and the silicon detectors are 50 or 70 eV type resolution at oxygen, the mission with the silicon detectors does a pretty good job here at the center, in the central 5 to 10 kiloparsecs of detecting the emission related to the galaxy and the disk. But you can see it sort of fades out into nothingness here as you get to the outskirts, again, where LEM can clearly detect the diffuse emission all the way out to R500, maybe even beyond. So this is science that basically cannot be done with an X-ray silicon-based detector. And it also cannot be done with a grating, because a grating will get a measurement essentially through one very narrow pencil beam, but it's not the same, of course, as being able to measure the whole, directly measure the image of the halo, the entire halo in one shot with many galaxies. So this is our programmatic overview. Essentially, the mission concept is being developed by a team of scientists at SAO and Goddard Space Flight Center, and we're in the process of trying to partner with somebody from industry to build the spacecraft and do other things. Most of the scientific instrumentation will be developed at Goddard, the X-ray optic and the cryogenic detectors. SAO will lead the science team and science center activities, and the industry partner, of course, will build the spacecraft, lead integration and testing, and lead mission ops. Science working groups have already developed a preliminary STM and defined the preliminary instrument requirements. We have significant international scientific interest in this concept at present. We have 60 scientists or so who are actively involved with the science working groups from across the globe. And I think it's fair to say that there's significant interest in LEM outside the X-ray astrophysics community. Joe Burchett here is going to talk a little bit about that later in the slides, or later in the discussion. One thing I want to mention, this is going to be a key component. Equity, diversity, inclusion obviously is a key component in the AO, that we're going to have to address this issue specifically in the context of the LEM mission. The LEM team, I want to emphasize, is committed to the principles of EDI, and this is going to be an important element of our proposal and a consideration of everything that we do. We already have some good ideas about how we want to promote LEM or promote EDI as part of the LEM mission if we go forward. One thing I will say is that in our org chart, we're going to have an EDI team that's going to have essentially parallel structure with the science team. So this will be a direct report to the mission PI. And so the EDI activities will have the highest level of both visibility and accountability in the mission. So this is going to be my final slide, and sort of ask this rhetorical question: can LEM win? I mean, in my personal opinion, yes, I think it can. I think it's very exciting. I think we've assembled a strong, proven team. We have a good combination of people who have proven the capability of building instruments. We have people that have proven the capability of operating large missions. And we have a very strong scientific team that can help develop the science program and analyze the science data once it comes to it. LEM is capable of delivering absolutely transformative science. This issue of structural formation, this is one of the big picture questions in all of astrophysics, okay? And it's not just me saying this, the Astro 2020 Decadal said this as well. We can deliver transformative science within the probe cost cap, and we'll also have a wide range of additional geo observations spanning all of X-ray astronomy. There's broad synergies with both ground-based and space-based observatories and other bands. And we have a lot of support already from the theorists who are working in Illustrious TNG, who are working in Eagle, Simba, Fire, all of the high-resolution galaxy formation simulations. One thing I want to emphasize, that there's still a great deal of work to do to define the LEM science case. And anybody who's still interested in getting involved, whether your science is relevant to the science here that's driving the STM or not, we definitely encourage you to reach out to us, and you're definitely welcome to participate. I want to just finish on one note here, a slightly personal note, and I'll be done now, okay? A few years ago, this was probably 10 years ago, I had the great opportunity to sit at an X-ray astronomy conference for the entire conference, to sit beside Ricardo. And I got his running dialogue about every talk for 3 or 4 days. This was an X-ray astronomy conference in Europe. And one of the things he would always say is, well, what's new? What did I learn? And this didn't change my view of the universe, okay? This talk wasn't very interesting. LEM, in critical ways, will change our view of the universe. Thank you. Questions?
Thank you very much, Ralph. We have time for one quick question as the speakers change. There will be more questions later, so.
Okay, yeah, looking at, this is a fabulous design concept, and be able to look at the line image and the line duration, that's great, actually. Question is, your simulation is for the 1 million second.
Yeah.
Suppose we want to do the similar thing in the nearby Robocraft galaxy, something like that. What would be the typical photo time or those kind of quality? So repeat the question for the.
Yeah. So we showed us essentially a simulation for 1 million second observation of a Milky Way-like galaxy, and the question was about other galaxies or clusters, other galaxies. Okay. So the exposure time depends. Sorry, there's two things. One, of course, this is based on a simulation, not necessarily reality. Okay. So there's some uncertainty about the flux there. But what I would say is that the more massive systems require less observation time, and it's a question of how deeply and how far out we feel like we need to go. So there's obviously all of these trade-offs here. The 1 million second observation is sort of a typical one that for a Milky Way-sized galaxy, we can easily get out to R500. And for more massive ones, we'll do a lot less observation. We might need to have some deeper observations for less massive halos. Okay.